Tonight, we're going to talk about the size of the universe, and when I say size, I don't mean the part astronomers can measure or the part that shows up in textbooks. I mean the whole thing, the actual thing. And here's what most people don't realize. Nobody knows how big that is, not even close. Step outside on a clear night, away from city lights, and look up. The sky is full of stars, thousands of them, visible to the naked eye, scattered across the dark in every direction. It feels enormous. It feels like you're seeing a long way. And compared to anything in your daily life, you are. But what you're seeing when you look up at that sky is almost nothing. A tiny sliver of a single galaxy, a fraction of the observable universe, let alone the universe itself. That gap between what the night sky feels like and what the universe actually is what this is about. Most people have heard the number. The observable universe is about 93 billion light-years across. That's the figure that shows up in documentaries, in textbooks, in science articles written for general audiences. And it is a staggering number. A light-year is about 5.88 trillion miles. Multiply that by 93 billion and you get something that no human brain can actually hold. The number is real. The scale is real. But here's what most people don't realize. That number isn't the size of the universe. It's the size of the part we can see. And those are very different things. The observable universe is a sphere centered on Earth, not because Earth is special, because we're the ones doing the observing. Every observer in the universe has their own observable sphere, centered on wherever they happen to be. An observer in a galaxy 10 billion light-years away has a completely different observable universe than we do, overlapping only partially with ours. What defines the edge of our observable universe isn't a wall or a boundary in space. It's time. It's the speed of light. We can only see regions from which light has had enough time to reach us in the 13.8 billion years since the Big Bang. Beyond that horizon, space continues. The universe continues. We just can't see it. This distinction is fundamental. The observable universe is shaped by physics, by the immutable speed of light, by the finite age of the cosmos. But nothing in those facts tells us where the actual universe ends. Beyond our cosmic horizon, regions of space certainly exist that are too distant for their light to have reached us yet. These regions are not speculative or hypothetical. They're a natural, inevitable consequence of how expansion and light travel work together. The universe beyond what we can observe is likely just as full of structure, galaxies, and complexity as the part we can measure but completely inaccessible to us. And when cosmologists try to estimate how much farther it goes, the numbers get strange fast. Some calculations suggest the whole universe is at least 10 to the power of 23 times larger than the observable portion. Some models suggest it's infinite, not very large, not unimaginably large. Infinite, extending in all directions without end, filled with galaxies and stars and empty space, forever. If that's true, then every number you have ever heard describing the size of the universe, 93 billion light-years, 2 trillion galaxies, 10 to the 24th stars, is not just an undercount. It's so far from the full picture that it barely qualifies as a description at all. That's what we're going to work through, step by step, scale by scale. We're going to start with Earth, with something you can picture. Then we're going to move outward, slowly at first, through the moon and the solar system and the nearest stars. Then faster, through the galaxy, through clusters and superclusters, through the full width of what we can observe. And then we're going to go further into what lies beyond the observable horizon, where the physics gets strange, and the honest answer to most questions is that we don't know. But here's what the evidence suggests. By the time we're done, you'll understand why every number that gets attached to the universe is almost certainly too small. You'll understand why the observable universe and the actual universe are separated by a gap that might be infinite. And you'll understand why cosmologists who spend their careers studying this describe it not as a solved problem, but as an open one of the deepest open questions in all of science. The universe is bigger than you think, not a little bigger, not twice as big. Bigger in a way that makes the word bigger seem inadequate. And the only way to understand what that means is to start where we always start, with something familiar, and then keep going until familiar becomes meaningless. Let's start with the moon, because the moon is the one object in the night sky that actually looks like something. Not a point of light, not a smear of color, an actual surface. You can see craters with the naked eye on a clear night. You can watch it move. You can track its phases week by week. Of all the objects in the sky, the moon is the one that feels almost reachable. And in cosmic terms, it basically is. The Earth itself is about 8,000 miles across. That's the diameter of the whole planet, the full width of the world you've lived on your entire life. If you could drive a car at highway speed straight through the Earth from one side to the other, it would take roughly 5 days. That's the size of our world. It's large by any standard we experience day to day, but it's a number we can at least begin to hold in our heads. The moon sits about 240,000 miles away. That's the average distance. It varies slightly because the moon's orbit isn't a perfect circle, but 240,000 miles is the number to work with. Compared to the width of the Earth, that's about 30 Earth diameters stacked end to end. If you drove there at highway speed, it would take roughly 6 months. The moon is the only world beyond Earth that human beings have ever physically stood on. 12 people walked on its surface between 1969 and 1972. No human has been back since. Light covers that distance in about 1.3 seconds. That's how we know so precisely how far away the moon is. Astronomers have bounced laser pulses off reflectors left behind by the Apollo missions and timed the round trip. The signal goes out, hits the moon, comes back. Just over 2.5 seconds total. That's how close the moon is in light travel terms. A fraction of a heartbeat. And yet getting humans there took 3 days. The Apollo astronauts weren't crawling. They were traveling at roughly 25,000 miles per hour at peak velocity. That's fast enough to circle the Earth in under an hour. At that speed, it still took 3 days to reach the moon. 3 days of coasting through empty space. The crew of Apollo 11 had time to sleep, eat, run system checks, and watch Earth shrink behind them before they ever saw the moon close up. Here's something worth sitting with for a moment. During those 3 days, the astronauts were farther from any other human being than any person in history had ever been. They were completely alone in a way that's hard to describe. No ocean voyage, no polar expedition. Nothing before or since has put human beings that far from the rest of their species. And they were only 240,000 miles out. In the context of what we're about to discuss, they hadn't gone anywhere at all. The moon is close enough that we can communicate with it in real time, more or less. There's a 1.3 second delay each way, so a conversation has a slight lag, but it's workable. Radio signals, television broadcasts, voice transmissions, all of it reaches the moon in about the time it takes to blink. When mission controllers in Houston talked to the astronauts on the lunar surface, the delay was barely noticeable. That's what 240,000 miles means in communications terms. Almost instant. But here's what starts to shift when you really look at this distance. The moon is 240,000 miles away, and it's the closest significant object to us in space. Everything else is farther, not a little farther. orders of magnitude farther. The distance to the moon, which required our most powerful rockets and 3 days of travel, is going to become the smallest unit of measurement we'll use for the rest of this video. By the time we're talking about the nearest stars, the distance to the moon will have shrunk so far into irrelevance that comparing it to interstellar distances is like comparing a single step to a walk around the entire planet. And that's the thing about space. It doesn't scale the way your intuition expects. You get used to one distance, and then the next one doesn't just add on top of it. It swallows the previous one entirely. The moon feels far. It is far by every measure available to human experience. But the universe doesn't care about human experience, and the numbers that come next don't ease in gently. They arrive all at once, and the moon disappears. 3 days to cross 240,000 miles, and in a few minutes, that number is going to disappear so completely it might as well be zero. The sun comes up every morning and fills the sky with light, and from down here on the surface, it's easy to forget that it's 93 million miles away. That number doesn't feel real. It can't. We have no frame of reference for 93 million miles. The farthest most people have ever traveled in their lives is a few thousand miles. 93 million is not an extension of that. It's a different category of distance entirely. Here's one way to feel it. Light travels at 186,000 miles per second. Nothing in the universe moves faster. And yet, when light leaves the surface of the sun, it takes about 8 minutes to reach us. 8 minutes at 186,000 miles per second. If the sun simply switched off right now, we wouldn't know for 8 minutes. We'd be standing in what felt like an ordinary morning, and the sun would already be gone. That's what 93 million miles actually means. Now keep going outward. Mars sits about 140 million miles from the sun on average. That number shifts because Mars and Earth are both moving, orbiting at different speeds, sometimes swinging closer together, and sometimes pulling far apart. At its farthest, Mars is over 250 million miles away from us. When NASA engineers send commands to a rover on Mars, they don't get instant responses. The signal travels at the speed of light, and even then it can take anywhere from 3 to 22 minutes to arrive. Then you wait just as long for a reply. A two-way conversation with Mars takes up to 44 minutes. That's not a delay. That's physics. Jupiter is 484 million miles from the Sun. Saturn sits at 886 million miles. These are planets we've visited with spacecraft. We've photographed Saturn's rings up close. We've watched storms churn on Jupiter for decades. And yet those planets are so far away that sunlight reaching Saturn is already 100 times dimmer than what we see here on Earth. Saturn doesn't look like it's bathed in sunlight. From Saturn's surface, the sun would look like an unusually bright star. Brilliant, but small. Cold. Neptune is the farthest major planet, orbiting at about 2.8 billion miles from the sun. A signal sent from Earth to Neptune takes roughly 4 hours to arrive, 4 hours at the speed of light. When Voyager 2 flew past Neptune in 1989, the closest it came was about 3,000 miles above the cloud tops. The images it sent back took over 4 hours to reach us. The scientists watching in real time weren't seeing what was happening. They were seeing what had already happened 4 hours earlier, 2.8 billion miles away. Most people picture the solar system as a kind of compact disk, planets spaced fairly evenly, everything relatively close together. That image is wrong. The solar system is almost entirely empty. The distances between objects are staggering compared to the sizes of the objects themselves. Here's a comparison that helps. If you shrank the sun down to the size of a grapefruit and set it on a table, Earth would be a pinhead sitting about 50 feet away. Jupiter would be a small marble, roughly 250 feet out. Saturn would be another marble at about 500 feet, and Neptune, still at grapefruit sun scale, would be a tiny dot sitting more than a mile away. 1 mile from a grapefruit, and that's still inside our solar system. The void between worlds is not a gap. It's the overwhelming reality. The planets are the exception. But all of that, every planet, every moon, every asteroid, every bit of space between Neptune and the Sun, is still just the inner solar system in a broader sense. Because there's something beyond Neptune that most people have never heard of, and it changes the picture entirely. Astronomers believe the solar system is surrounded by an enormous spherical shell of icy objects called the Oort cloud. It isn't a tight ring like the asteroid belt. It's a vast, diffuse halo extending in every direction, beginning somewhere around 2,000 astronomical units from the Sun and stretching outward to perhaps 100,000 astronomical units or more. 1 astronomical unit is the distance from Earth to the Sun. So we're talking about a shell of material that begins 2,000 times farther from the Sun than we are, and extends to 100,000 times that distance. In light travel time, the outer edge of the Oort cloud is roughly 1.5 to 2 light years from the Sun. 2 light years. Light, which crosses our entire planet in a fraction of a second, which covers the 93 million miles from the Sun to Earth in 8 minutes, would need 2 years to cross from the Sun to the edge of our own solar system. This is still our solar system. These icy objects out there are still gravitationally bound to our Sun. They still orbit it, though their orbits take millions of years to complete. Occasionally, one gets nudged by a passing star or the gravitational pull of some distant object, and it begins a long, slow fall toward the inner solar system, eventually becoming a long-period comet. Those comets with their bright tails are visitors from the outermost edge of our own neighborhood. Nobody has directly observed the Oort cloud. It's too far, the object's too small and too dark. We know it almost certainly exists because of the comets it produces, and because the physics demands it. But we've never photographed it. We've never seen it. It's inferred. And here's the thing that makes the Oort cloud so important as a reference point. We've actually sent a spacecraft in roughly that direction. It's been traveling for nearly half a century. It's the fastest human-made object ever launched, and it hasn't come close to reaching the Oort cloud yet. It won't for hundreds of years. At the speed we managed to achieve, crossing just our own solar system takes longer than human civilization has existed in any recognizable form. The edge of our own solar system is already so far that we haven't reached it, and everything we're about to talk about begins on the other side of that boundary. In 1977, NASA launched a spacecraft called Voyager 1, and it has been moving away from Earth every single second since. It launched on September 5th of that year. It flew past Jupiter in 1979. It passed Saturn in 1980. Then it kept going. No destination, no stopping point. Just the void and the steady push of the momentum it built during those early planetary flybys. For nearly 5 decades, Voyager 1 has been falling outward through space at roughly 38,000 miles per hour. That's fast by any standard we use on Earth. Commercial jets fly at about 575 miles per hour. A rifle bullet travels at around 1,700 miles per hour. Voyager is moving at more than 22 times the speed of a bullet, and it has been doing so continuously since before most people watching this were born. As of the most recent measurements, Voyager 1 is about 15 billion miles from Earth. That number is worth sitting with. 15 billion miles. It's roughly 167 times the distance from Earth to the Sun, which astronomers call 1 astronomical unit. In those terms, 167 astronomical units sounds like a lot. It sounds like Voyager has gone somewhere genuinely remote, and by human standards, it absolutely has. No object built by human hands has ever traveled farther. Nothing we've made has ever been more distant from the planet where it was created. 15 billion miles is the farthest we've ever reached, and it represents the physical boundary of human exploration. But here's what that distance actually means in cosmic terms. 1 light year is about 5.88 trillion miles. Voyager is 15 billion miles out. That puts it at roughly 0.0026 light years from Earth. Not 2.6 light years. Not 0.26 light years. 0.0026. To cross a single light year at Voyager's current speed would take approximately 17,000 years. Voyager hasn't covered a single light year yet. It hasn't covered a tenth of one. It hasn't covered a hundredth. After 47 years of constant travel, Voyager 1 is still, in any meaningful astronomical sense, right here. The Sun's gravitational influence extends far beyond where Voyager sits now. The heliosphere, the bubble of solar wind that the Sun inflates around itself, has a boundary called the heliopause. Voyager crossed that boundary around 2012, which made headlines. It entered interstellar space. That was real. The particle environment changed. The magnetic field shifted. Voyager was genuinely outside the zone where the Sun's solar wind dominates. But the Sun's gravity doesn't stop at the heliopause. The Oort cloud, that vast shell of icy objects described in the previous section, extends perhaps 1 to 2 light years in every direction. In the strictest gravitational sense, Voyager is still inside our solar system. It will be inside our solar system for another 300 years before it even reaches the inner edge of the Oort cloud. And crossing the Oort cloud entirely will take roughly 30,000 years. So when we say Voyager is at the edge of the solar system, we have to be careful about what we mean. It's at the edge of the Sun's wind. It's in interstellar space by one definition. But by the broader definition, the gravitational one, it has a very long way to go. Now consider this. The nearest star system to our Sun is Alpha Centauri, sitting about 4.24 light years away. At Voyager's current speed, reaching Alpha Centauri would take approximately 75,000 years. Not 75,000 miles from where it is now. Not 75,000 hours. 75,000 years. Modern human civilization is roughly 10,000 years old. We'd need to travel 7.5 full lengths of recorded human history just to get to the closest star. And Voyager isn't even heading toward Alpha Centauri. It's traveling in a completely different direction, toward the constellation Ophiuchus. The nearest star in that general direction is a dim red dwarf called Ross, 248, about 10.3 light years away. At Voyager's pace, it'll make its closest approach to Ross 248 in about 40,000 years. Closest approach, not arrival. It won't stop. It will sail past at a still enormous distance and continue outward. There are no stars within range of Voyager on any human timescale. There are no destinations waiting for it. It's carrying a golden record with sounds and images from Earth, a message for any intelligence that might one day intercept it. But the honest mathematical reality is that Voyager will drift through interstellar space for billions of years before it comes close to anything. Our galaxy is mostly empty. Stars are rare. The distances between them are so large that even a probe moving at tens of thousands of miles per hour barely registers movement against them. This is what makes interstellar distance so genuinely difficult to accept. We built something, launched it with everything we had, and watched it travel for nearly half a century. And the nearest star is still 75,000 years away at that speed. Our brains want to find a comparison that makes this feel manageable. There isn't one. The numbers don't convert into anything familiar. They just sit there, enormous and indifferent. Voyager 1 is a triumph of engineering. The fact that we can still communicate with it, that signals traveling at the speed of light take about 22 hours to make a round trip between Earth and the spacecraft, is genuinely remarkable. But it's also a reminder of exactly how small our reach actually is. We sent our farthest object into the universe, and the universe barely noticed. 47 years of travel, 15 billion miles covered, and we haven't even crossed the street in cosmic terms. The nearest star to our sun is a dim red dwarf called Proxima Centauri, and it is 4.24 light-years away. That number sounds clean, it sounds manageable, but let's figure out what it actually means. A light-year is the distance light travels in a full year. Light moves at 186,000 miles per second. In 1 year, it covers about 5.88 trillion miles. Multiply that by 4.24, and the distance to Proxima Centauri works out to roughly 25 trillion miles. 25 trillion miles to the nearest star. Not the far side of the galaxy. Not some distant object at the edge of the universe. The closest one. To reach Proxima Centauri at the speed of light, you'd need 4 years and a few months. 4 years of traveling at the fastest speed anything in the universe can travel. We spent a full section talking about Voyager 1, how it's been moving for nearly 50 years and covered about 15 billion miles. Proxima Centauri is 25 trillion miles away. That means Voyager, at its current speed, would need roughly 75,000 years to reach it. Not 75,000 miles, not 75,000 days, 75,000 years. Voyager isn't even heading in that direction, but even if it were, the people who built it, the people who launched it, every person alive today, every person who will ever live in any foreseeable future, would be long gone before it arrived. Here's a way to feel this distance more directly. Imagine shrinking the solar system down so the sun is the size of a basketball. On that scale, Earth is a small bead sitting about 26 feet away. Neptune, the outermost major planet, is about a quarter mile from the basketball. The whole solar system, from the sun out to Neptune, fits within a quarter mile. Now, on that same scale, where is Proxima Centauri? It's another basketball sitting roughly in Los Angeles. If the sun is a basketball in New York City, the nearest star is a basketball in Los Angeles. And between them, nothing. No planets, no stations, no waypoints. Just empty space for the entire width of a continent. At the speed of light, you can cross the solar system in a matter of hours. 8 minutes to reach Earth from the sun, about 4 hours to reach Neptune. The solar system feels large when you're thinking about spacecraft travel times. But then you turn and face interstellar space, and the solar system shrinks to almost nothing. 4 years at the speed of light just to reach the closest star. Our fastest spacecraft would need 75,000 years. The scale change is not gradual, it's a cliff. Now consider what it means to see Proxima Centauri in the sky tonight. The light reaching your eyes right now left that star about 4 years ago. You're not seeing Proxima Centauri as it is, you're seeing it as it was 4 years in the past. That gap is small by the standards of what's coming, but it's real. The star could have changed in the last 4 years, and we wouldn't know yet. That's not a flaw in our instruments. It's a fundamental feature of how light works. There's no way around it. Looking at distant objects in space is the same as looking back in time. Proxima Centauri is part of a 3-star system. The other 2 members, Alpha Centauri A and Alpha Centauri B, orbit each other and are slightly farther away at about 4.37 light-years. These 3 stars are our nearest neighbors, and they're still separated from us by more than 25 trillion miles. The next nearest stars after that are also in the range of several light-years away. Barnard's star is about 6 light-years out. Sirius, the brightest star in the night sky, sits about 8.6 light-years away. The light from Sirius that you see tonight left that star more than 8 years ago. On a clear night with no moon and no light pollution, the human eye can pick out somewhere around 5,000 stars. Those stars are not all at the same distance. The nearby ones are a few light years away. The more distant ones visible to the naked eye push out to around 1,500 light years. That means the light from the most distant of those naked eye stars has been traveling toward you for 1,500 years. When that light started its journey, the Roman Empire had already fallen. The Middle Ages were just beginning. That ancient light is now entering your eye on an ordinary evening while you stand in a backyard or on a sidewalk. And that's still just the naked eye limit. Extend your view slightly and things get more extreme. The farthest single star visible to the naked eye under exceptional conditions sits at roughly 16,000 light years from Earth. The light you'd be seeing from that star left before the last ice age ended, before agriculture existed anywhere on Earth, before humans had built a single permanent structure. That light has been crossing space ever since, and it reaches your eye looking no different from the light of a nearby star. There's no way to tell by looking which light is ancient and which is recent. The night sky is a mosaic of different moments in time, all arriving simultaneously. This idea that looking at stars is looking backward in time starts to feel philosophical. But it isn't. It's physics. Light takes time to travel. That time represents real delay. When we look at a star 1,000 light years away, we are seeing that star as it was 1,000 years ago, with no exceptions and no workarounds. The star we see might not even exist anymore. It could have exploded 500 years ago, and the light from that explosion is still 500 years away from us. We'd have no way to know. Distance and time are the same thing when you're talking about light, and every distance we've measured from here forward will carry that implication with it. The interstellar distances between even the nearest stars are enormous enough to make human travel essentially impossible with anything we can currently build or reasonably imagine building. And yet these nearby stars, 4, 8, 15 light years away, are our immediate neighbors. They're the closest points on a map that extends outward for 100,000 light years just within our own galaxy. Every star you've ever looked at is a glimpse into the past, and the farther away it is, the deeper into history you're seeing. And we've barely started. The Milky Way is the galaxy we live in, and most of us have never actually seen it properly. Light pollution has erased it from the sky above most cities. You'd need to drive hours from the nearest major city, find genuinely dark ground, and let your eyes adjust for 20 minutes before it appears. When it does, it looks like a pale smear of light stretching across the sky from horizon to horizon. Not individual stars, a cloud, a band of faint luminosity so diffuse it seems almost imaginary. What you're actually seeing is the combined light of hundreds of billions of stars, so distant and so densely packed in that direction that they blur together into a single glow. That glow is our galaxy seen from the inside. We live inside it, roughly 2/3 of the way out from the center, embedded in one of its spiral arms. From this position, looking toward the core, we're staring into the densest region of the galaxy. Looking away from the core, we're looking outward toward the edges. We can't step outside and see the whole thing the way we can photograph another galaxy. Everything we know about the Milky Way's shape, we've had to figure out the way you'd figure out the floor plan of a house you've never left. The Milky Way is roughly 100,000 light years across. At our location, it's about 1,000 light years thick. That thickness sounds like a lot until you compare it to the width. It's a flat disk, essentially. A spinning plate of stars and gas and dust with a dense bulge at the center and spiral arms curling outward from that bulge. Our solar system sits on the inner edge of one of those arms, the Orion arm, about 27,000 light-years from the galactic center. We are not at the center. We are not near the center. We sit in the outer suburbs of a vast, slowly rotating city of stars. To cross the Milky Way at the speed of light would take 100,000 years. Not 100,000 miles. 100,000 years of travel at 186,000 miles per second. The Voyager spacecraft, which has been moving away from Earth for nearly 50 years, travels at about 38,000 miles per hour. At that speed, crossing the Milky Way would take roughly 1.7 billion years. These numbers aren't metaphors, they're measurements. The galaxy is simply that large. Our solar system orbits the galactic center. Everything in the Milky Way is in motion, rotating around the core in a slow, stately circuit. Our solar system completes one full orbit every 240 million years. That period has a name: the galactic year. We are currently about 20 galactic years old as a solar system. The last time Earth was in the same position relative to the galaxy, the Triassic period was just beginning. Dinosaurs were just emerging. The continents were arranged differently. The atmosphere had a different composition. And we've traveled exactly one full orbit since then. Go back 2 galactic years, 480 million years, and you reach the Cambrian explosion, the moment when complex animal life first proliferated in Earth's oceans. Everything that has ever lived on this planet, every species that has ever existed, every mass extinction and recovery, every ice age and warm period, all of it has happened within 2 orbits of the galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range is large because counting them precisely is genuinely difficult. Stars are obscured by dust. Many are dim. We can estimate their numbers by measuring the galaxy's mass and accounting for the known distribution of stellar types. But the uncertainty remains wide. Even the lower estimate is nearly impossible to hold in your mind. 100 billion. 100,000 million stars, each one a sun, many of them larger than our own, each potentially surrounded by its own system of planets. If every star in the Milky Way were a grain of sand, you'd have enough sand to fill a beach. Not a handful, not a jar. A full-scale beach stretching for miles, piled deep. That's what 100 billion of anything looks like in physical terms. And that's the lower estimate. The galactic center is a different environment entirely from the quiet outer arm where we live. The density of stars near the core is far higher. There are regions of intense radiation. At the very center sits a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. It's not actively consuming material at a dramatic rate right now, but its gravitational influence shapes the motion of everything around it for thousands of light years in every direction. The stars orbiting closest to Sagittarius. A star complete their orbits in just a few years. Some of them are moving at a few percent of the speed of light, whipping around an invisible point that contains more mass than 4 million suns compressed into a region smaller than our solar system. Between the stars, the galaxy is not empty. It's filled with gas and dust, raw material left over from previous generations of stars and expelled by new ones. This interstellar medium is thin by any laboratory standard. In most regions, it's far less dense than the best vacuum we can create on Earth. But it's vast, and it's the material from which new stars are still being born. The Milky Way is not a finished structure. It's an ongoing process. Stars are forming right now in dense molecular clouds scattered throughout the disk. Other stars are dying, shedding their outer layers or collapsing under their own gravity. The galaxy we see tonight is not the galaxy that existed a billion years ago, and it won't be the same galaxy a billion years from now. From the outside, the Milky Way would look something like the Andromeda galaxy, our nearest large neighbor. A flat spiral disk with a bright central bulge, arms trailing outward in sweeping curves. A faint halo of older stars surrounding the whole structure. It's a barred spiral galaxy, meaning the central bulge stretches into an elongated bar shape rather than a simple round core, with the spiral arms emerging from the ends of that bar rather than directly from the center. The Milky Way is not a particularly impressive galaxy by cosmic standards. There are galaxies dozens of times larger. There are galaxies containing trillions of stars. There are elliptical galaxies so massive that our entire galaxy would be a modest addition to their outer edges. The Milky Way is a medium-sized spiral galaxy, average in most respects, orbiting no particularly special region of space. It just happens to be the one we live in. And we don't live in it alone. The Milky Way is part of a collection of dozens of galaxies spread across millions of light years, bound together by gravity, moving through space as a unit. Our galaxy is the second largest member of this group, trailing only the Andromeda galaxy in size. But the group itself, vast as it is, sits within something larger still. 100 billion stars, 100,000 light years across, and it's just one member of a group, which is itself just one node in something almost too large to describe. The Milky Way doesn't exist alone. It's part of a larger collection of galaxies called the Local Group, and the Local Group spans roughly 10 million light years across. There are about 80 galaxies in it. Most of them are small, dwarf galaxies, irregular galaxies, faint collections of stars that barely register next to the two dominant members. And those two dominant members are the Milky Way and the Andromeda galaxy. Andromeda is the one most people have heard of. It sits about 2.5 million light years away. That number is almost impossible to hold in your head after the distances we've already covered, but here's what makes it different from everything else in this discussion. You can see Andromeda with your bare eyes. On a clear, dark night, away from city lights, it appears as a faint smudge in the constellation Andromeda. No telescope required. It's the most distant object a human being can see without any instrument at all. That smudge of light is 2.5 million light years away. The light entering your eyes right now left Andromeda 2.5 million years ago. Modern humans didn't exist yet. Our ancestors were early hominids in Africa, making stone tools with no concept of fire, agriculture, or language as we understand it. And that light has been traveling through empty space ever since, crossing 2.5 million light years, arriving at your eyes on an ordinary night. What makes this remarkable is that Andromeda is the only distant galaxy visible without instruments. Its prominence results from both its size and favorable orientation. The disk is angled correctly for its light to reach us. Andromeda is not a small galaxy. It's actually slightly larger than the Milky Way. Where the Milky Way spans roughly 100,000 light years across, Andromeda stretches about 220,000 light years. It contains over 1 trillion stars. That's more than twice the number in the Milky Way by some estimates. The two galaxies are the giants of the Local Group, and everything else orbits around or between them. Smaller galaxies cluster near each of them like satellites. Some are so small and faint they were only discovered in recent decades. The Milky Way has its own set of satellite galaxies. The most well-known are the Large and Small Magellanic Clouds, visible from the southern hemisphere as bright patches in the night sky. The Large Magellanic Cloud is about 160,000 light years away. The Small Magellanic Cloud is about 200,000 light years out. Both are irregular galaxies, smaller and less structured than the Milky Way, but they contain hundreds of millions of stars each. They orbit our galaxy slowly, pulled along by its gravity, gradually being stripped of material as they move. There are other satellite galaxies too, fainter ones. The Sagittarius dwarf spheroidal galaxy is so close and so stretched out by tidal forces that it's actually being absorbed into the Milky Way right now. Its stars getting pulled into our galactic disk over hundreds of millions of years. Andromeda and the Milky Way are not going to stay separated forever. They're moving toward each other. The two galaxies are approaching at roughly 70 miles per second, and in about 5 billion years, they will collide. That might sound violent, but the collision will be slow. It will take hundreds of millions of years to play out. The stars inside each galaxy are spread so far apart that actual stellar collisions will be rare. What happens instead is that gravity reshapes both galaxies. Stars get flung into new orbits. The spiral arms get disrupted. Over a very long time, the two galaxies will merge into a single larger elliptical galaxy. Some astronomers have already started calling the result Milkomeda. The Sun will likely survive. Earth, if it still exists, will likely survive too, though it may end up in a completely different region of the new combined galaxy. This slow merger will reshape both galaxies dramatically. Gravitational forces will disrupt their elegant spiral arms. Stars will be torn from their orbits and cast into new paths. The collision will spark intense star formation as gas clouds collide and compress. Eventually, the chaos settles into a new, rounder galaxy. But here's the scale of the local group itself. It spans 10 million light years. 10 million. We established earlier that the Milky Way is 100,000 light years across. The local group is 100 times wider than the galaxy it contains. Voyager 1, the fastest spacecraft ever launched, is currently traveling at about 38,000 miles per hour. At that speed, it would take roughly 75,000 years just to reach the nearest star. To cross the local group at that speed would take approximately 200 billion years. The universe is only 13.8 billion years old. We could launch every spacecraft ever built, pointed in the same direction, and not one of them would come close to crossing the local group within any timeline that has any human meaning. The local group also sits within a larger context. It's not floating in isolation. The nearest major galaxy cluster, the Virgo cluster, is about 54 million light years away. The local group is falling slowly toward it, drawn by the immense gravitational pull of all those galaxies concentrated in one region. We're moving, right now, in that direction. Not fast enough to ever reach it on any human timescale, but moving nonetheless. The local group is a gravitationally bound system. The galaxies inside it will not be pulled apart by the expansion of the universe. They're held together. But the universe beyond them is expanding, and the clusters and superclusters beyond the local group are separating from us, growing more distant over time. 80 galaxies, 10 million light years. Two dominant spirals on a collision course billions of years from now. Satellite galaxies orbiting each of them, dwarf galaxies scattered throughout, and the whole thing is still just a neighborhood. A bounded, local, relatively quiet pocket of space. 10 million light years of space, dozens of galaxies, and it's a small, quiet corner of something far larger. Between the local group and the nearest major collection of galaxies, there is mostly nothing. Not mostly empty in the way that interstellar space is empty, where you still have the occasional gas cloud or stray particle. Genuinely, almost completely nothing. Tens of millions of light years of space containing no galaxies, no significant clusters of stars, no structure worth naming. Just void. Most people, when they think about the universe, picture it as a kind of crowded place. Galaxies scattered everywhere, stars filling the dark. But that picture is wrong. The vast majority of the universe's volume is void. If you could somehow travel from the local group outward in a random direction, the odds are good that you would cross tens of millions of light years before encountering another significant collection of galaxies. The universe is, structurally speaking, mostly empty space with thin walls of matter surrounding enormous bubbles of nothing. The nearest major cluster of galaxies to us, the Virgo cluster, sits about 54 million light-years away. Between the edge of the local group and Virgo, there is very little. The local group itself spans about 10 million light-years. That means the gap between where our galactic neighborhood ends and where the next major structure begins is something like 40 million light-years across. Light takes 40 million years to cross that gap. Our entire local group, with its dozens of galaxies and its 2.5 million light-year distance from us to Andromeda, would fit inside that void roughly 4 times over. And yet, even this void isn't the point. The point is what exists on the other side of it. Because when you start examining the galaxies beyond our local neighborhood, something uncomfortable becomes clear. Everything we've described so far, every galaxy we've walked through, starts to look very small. IC 1101 is a galaxy sitting about 1.04 billion light-years from Earth. It's the largest known galaxy in the observable universe. Its diameter is estimated at roughly 6 million light-years. Our own Milky Way, at 100,000 light-years across, fits into IC 1101 about 60 times along a single straight line. In terms of volume, the comparison is almost meaningless to state. IC 1101 contains an estimated 100 trillion stars. The Milky Way contains somewhere between 100 billion and 400 billion. IC 1101 holds roughly 250 times as many stars as our entire galaxy. It's not a bigger version of the Milky Way, it's a different category of object entirely. IC 1101 is what astronomers call a supergiant elliptical galaxy. It has no spiral arms, no disk. It's a vast, roughly spherical cloud of stars, ancient and dense at its center, extending outward for millions of light-years in every direction. The stars near its core are packed together far more tightly than anything in our galaxy's center. Its core alone, the dense inner region, is wider than the entire Milky Way. There's a pattern here that keeps repeating. Earth seemed enormous until you put it next to the solar system. The solar system seemed vast until you measured it against the distance to the nearest star. The Milky Way, with its hundreds of billions of stars, seemed almost incomprehensibly large, and then you placed it next to IC 1101. At every step, the previous scale collapses. What seemed like an endpoint turns out to be a detail. Astronomers see this pattern repeated throughout the universe. Beyond the local group, individual galaxies range wildly in size. Some are dwarf galaxies smaller than the Magellanic Clouds, containing only a few billion stars. Others are massive ellipticals containing trillions. The range between the smallest and the largest galaxy is enormous, spanning several orders of magnitude. IC 1101 sits at the extreme end of that range. Its 6 million light-year diameter is roughly 60 times the diameter of the Milky Way and more than 27 times the diameter of Andromeda. If IC 1101 sat where the Milky Way sits now, its outer edges would extend past most of the local group's member galaxies. But even IC 1101 is not the organizing unit at this scale. Galaxies, even giants like IC 1101, don't sit alone. They exist within clusters. Clusters of hundreds or thousands of galaxies, all bound together by gravity, all embedded in vast amounts of dark matter and hot gas. IC 1101 itself sits at the center of a cluster called Hubble 2029. Hubble 2029 contains hundreds of galaxies. IC 1101 is the largest of them, the gravitational anchor, the dominant object. And yet it shares that cluster with hundreds of other galaxies, each one a collection of billions or trillions of stars, each one a structure that would have seemed incomprehensible from the perspective of our solar system. The void between galaxy groups is not empty because matter is rare. It's empty because matter at this scale organizes into structures, walls, and filaments and dense nodes, and leaves the space between those structures genuinely bare. Galaxies, even monstrous ones, are not scattered uniformly through space. They cluster, they clump. They pull each other inward through gravity and form associations that are themselves enormous. And those associations are the next step in the structure. And I see 1101, that monstrous galaxy 6 million light-years across, is itself just one member of a galaxy cluster containing hundreds more. Galaxy clusters are the largest structures in the universe held together by their own gravity, and they make everything we've talked about so far look modest. Not just a little more impressive, not a noticeable step up. We're talking about a completely different category of object, the kind where the numbers stop connecting to anything your mind can picture and start functioning purely as symbols. The nearest major cluster to us is the Virgo cluster, sitting about 54 million light-years away. The light reaching us from the Virgo cluster tonight left those galaxies before our earliest primate ancestors existed, before the continents looked the way they do now. That's how far away the nearest major cluster is, and it contains over 1,300 individual galaxies. Not 1,300 stars, not 1,300 solar systems. Galaxies, each one home to hundreds of billions of stars. The Virgo cluster spans roughly 8 million light-years across its core region. To cross it at the speed of light would take 8 million years. Our entire local group, with its dozens of galaxies spread across 10 million light-years, would fit inside the Virgo cluster's membership and account for a tiny fraction of it. The Coma cluster is another example. It sits about 320 million light-years away and contains over 1,000 galaxies packed into a region roughly 20 million light-years across. The galaxies in the Coma cluster are densely grouped compared to our neighborhood. Where our local group has a few dozen members, the Coma cluster has thousands. And both of these clusters are considered fairly ordinary examples of the type. Now here's where it gets stranger. If you could somehow see the space between the galaxies inside a cluster, you'd find it isn't empty. It's filled with gas. Hot gas, heated to temperatures of tens of millions of degrees by the enormous gravitational energy of the cluster. This gas radiates in X-ray light, completely invisible to human eyes, detectable only by space-based X-ray telescopes. The gas permeates the entire cluster in a vast diffuse cloud. It doesn't glow in visible light. It doesn't show up in ordinary photographs. But it's there, and it's massive. The total mass of this hot gas spread between the galaxies actually exceeds the combined mass of all the visible galaxies in the cluster. The galaxies you can see are not the dominant form of matter. The invisible gas outweighs them, and yet even the gas isn't what holds the cluster together. That job falls to dark matter. Dark matter is invisible. It doesn't emit light. It doesn't reflect light. It doesn't interact with light at all. We can't see it directly. What we can see is its gravitational effect on everything around it. Galaxies inside clusters move faster than they should if only the visible matter were present. The hot gas is hotter and more compressed than it should be. The way clusters bend light from more distant objects behind them reveals mass far exceeding what any telescope can detect. All of that points to enormous halos of dark matter surrounding and permeating each cluster. In a typical cluster, dark matter accounts for roughly 85% of the total mass. The galaxies, the stars, the gas, everything we can observe makes up the remaining fraction. Dark matter is the invisible scaffolding the whole structure hangs from. The discovery of dark matter within clusters fundamentally changed how astronomers understood the universe's composition. Observations revealed that the universe contained far more matter than was visibly apparent, suggesting an invisible component outnumbering all stars and gas by a factor of 5 or more. This realization cascaded through cosmology, forcing a complete revision of models about how galaxies form and evolve. It became clear that visible matter was merely the glowing tip of an enormous invisible iceberg. Dark matter's influence extended far beyond individual clusters, shaping the structure of the entire cosmos. The presence of this invisible substance raised profound questions about the fundamental nature of reality itself. A teaspoon of that hot intracluster gas would contain only a handful of particles. By laboratory standards, that's essentially a vacuum. The gas is extraordinarily thin, spread across millions of light years, and yet integrated across the full volume of the cluster. It represents more mass than all the visible galaxies combined. Our brains aren't built to hold both of those facts at once. Almost nothing, but stretched across an almost incomprehensible volume, becomes something enormous. The Virgo cluster is the gravitational anchor of the Virgo Supercluster, a larger structure that includes our own local group. We are not simply near the Virgo cluster. We are, in a sense, loosely bound to it. Our local group sits on the outskirts, moving slowly in the cluster's direction, though far too distant to be part of the cluster proper. The entire local group, with Andromeda, the Milky Way, and all its smaller member galaxies, would appear as a small peripheral grouping if you mapped it against the full extent of the Virgo cluster's population. Drop it into the cluster's membership and count. Over 1,300 galaxies, and our entire local neighborhood accounts for a few dozen of them. Clusters also aren't isolated. They sit at the nodes of the cosmic web, connected by filaments of galaxies and separated by enormous voids. The Virgo cluster isn't just a cluster on its own, it's a concentration point in a larger network. Other clusters nearby include the Centaurus cluster, the Perseus cluster, the Fornax cluster. Each one contains hundreds to thousands of galaxies. Each one is bound together by gravity and dark matter, filled with X-ray emitting gas, and embedded in a structure that dwarfs even the clusters themselves. Our local group doesn't belong to a cluster in the formal sense. We sit in a relatively underdense region of space, a quieter neighborhood between the larger concentrations. And even so, the nearest major cluster is still the gravitational dominant feature of our broader region of the universe. Everything nearby organizes itself around it. The Virgo cluster spans 8 million light-years and contains over 1,000 galaxies, and it's just one cluster among tens of thousands in the structure above it. In 2014, a team of astronomers mapped the supercluster our galaxy belongs to for the first time and gave it a name, Laniakea, which means immeasurable heaven in Hawaiian. The name fits. Laniakea spans about 520 million light-years. It contains roughly 100,000 galaxies. Everything we've talked about so far, the Milky Way, the local group, the Virgo cluster with its 1,300 member galaxies, all of it sits inside this one structure. To put that in perspective, the local group spans about 10 million light-years. Laniakea is 52 times larger than that in radius, and unlike the galaxy clusters we just covered, Laniakea isn't held together by gravity in the traditional sense. Galaxy clusters are gravitationally bound. They're locked in place, their members orbiting a common center of mass the way planets orbit a star. Laniakea is something different. It's organized by the large-scale flow of matter through space, rivers of galaxies streaming through the universe, pulled by concentrations of mass too enormous to fully map. To understand Laniakea's shape, think of it as a vast, irregular web of filaments. Galaxies and galaxy clusters aren't scattered through it at random. They run along threads like water droplets clinging to the strands of a spider's web. Those threads don't point outward in all directions. They point inward, all of them. The filaments of Laniakea converge on a single region called the Great Attractor, a massive concentration of mass sitting roughly 250 million light-years from us. Our entire local group is drifting toward it right now, pulled at about 1.4 million miles per hour. Not toward the edge of Laniakea, toward its center. We've been in motion toward it for billions of years and will keep moving toward it for billions more. The Great Attractor is difficult to study directly. It sits behind the plane of the Milky Way, hidden by the dense gas and dust of our own galaxy. For a long time, astronomers knew something was pulling matter in our direction but couldn't see what it was. They called the region the zone of avoidance because our own galaxy blocked the view. It took infrared and X-ray observations to penetrate that obscuring band and get a clearer picture of what lay behind it. What they found was a dense concentration of galaxy clusters, anchoring the inward flow of material across hundreds of millions of light-years. Our position within Laniakea is not central. We're nowhere near the Great Attractor. The Milky Way sits on the outer edge of the structure, near one of the fainter tendrils feeding into it. The Virgo cluster, about 54 million light-years away, is far closer to the heart of Laniakea than we are. If Laniakea were a continent, we'd be somewhere on the coastline, and the Great Attractor would be deep in the interior. The flow of galaxies across Laniakea is slow by human standards, but immense in scope. Thousands of galaxies moving together, drawn by the same gravitational gradient, threading through a structure 500 million light-years across. Andromeda is part of Laniakea. The Virgo cluster is part of Laniakea. The dozens of smaller galaxy groups scattered around our local group are all part of Laniakea. When astronomers first produced a map of this structure in 2014, they traced the velocity flows of thousands of galaxies and drew the boundary where those flows reversed, where galaxies were no longer drifting toward the Great Attractor, but were instead part of some other supercluster's pull. That boundary defines Laniakea's edge. Everything inside it moves, however slowly, toward the same center. The 2014 mapping required tracing the velocity flows of thousands of galaxies to determine precisely where Laniakea's gravitational pull ended and other forces took over. Astronomers analyzed redshift data, looking for subtle shifts indicating a change in dominant gravitational flow. This revealed not just Laniakea's extent, but also its internal structure, showing how galaxies cluster more densely along filaments than in the spaces between them. The boundaries they drew represent the cosmic watersheds where flows diverge, 520 million light-years across. And it's not the largest supercluster we know of, not even close. The Shapley supercluster, sitting about 650 million light-years away, is several times more massive. It may actually be contributing to the same large-scale pull that defines the Great Attractor region. Astronomers are still working out exactly how these structures connect. But the basic picture is clear. Laniakea is one of many superclusters distributed across the observable universe. Some are larger, some are smaller. They're not isolated from each other. They're linked. Matter flows between them along filaments, and between those filaments, there are voids, vast, nearly empty regions of space where almost no galaxies exist. Here's what most people don't realize. A supercluster is not an object the way a star or a galaxy is an object. It has no hard edge. It has no clear inside or outside the way a galaxy cluster does. It's a region of the universe defined by motion, by the direction matter happens to be flowing at this moment in cosmic history. Laniakea exists because the galaxies within it are all being drawn toward the same gravitational sink. But dark energy is working against this. The accelerating expansion of the universe is slowly pulling these structures apart. Over time, the coherence of superclusters like Laniakea will weaken. The outer tendrils will eventually stop flowing inward and start being carried away by the expansion of space itself. What we're seeing today is a snapshot, a temporary configuration in the long history of the universe's structure. We live in a galaxy, inside a galaxy group, inside a galaxy cluster's gravitational neighborhood, inside a supercluster 500 million light-years wide that is itself just one feature in something even larger. Each layer swallows the one below it completely. 520 million light-years of galaxies, all drifting toward the same gravitational center. And Laniakea is just one thread in a web that covers everything we can see. If you could somehow step back far enough to see all the galaxy clusters and superclusters at once, millions of them spread across hundreds of millions of light-years, you'd see something no one expected. Not a random scattering of galaxies. Not a uniform fog of matter spread evenly through space. What you'd see is a web. A vast three-dimensional network of filaments and sheets and dense nodes wrapped around enormous empty bubbles of almost nothing. It looks like a spider web stretched across the cosmos. It looks like the neural network of a brain. It looks like soap bubble foam, where the galaxies trace the thin walls between bubbles and the interiors of those bubbles contain almost nothing at all. Astronomers call it the cosmic web, and it is the largest structure we have ever mapped. The filaments are the strands of this web. They are long chains of galaxies and dark matter stretching across hundreds of millions of light-years, connecting clusters and superclusters the way threads connect the anchor points of a spider's construction. At the nodes where filaments intersect, you find the densest concentrations of matter in the universe. The massive galaxy clusters we talked about before, places like the Virgo cluster and the Coma cluster, regions where thousands of galaxies pile together under their mutual gravity. The filaments feed these nodes. Matter flows along them slowly, on timescales measured in billions of years, drifting inward toward the gravitational centers at each junction. Between the filaments, there is almost nothing. These regions are called voids, and they are genuinely staggeringly empty. A typical void spans somewhere between 100 million and 400 million light-years across. That's not a region with fewer galaxies. That's a region with almost no galaxies at all. The matter that once occupied these spaces was pulled away over billions of years, drawn by gravity toward the denser filaments surrounding each void. What's left behind is a near vacuum on a scale that's almost impossible to express. If you traveled in a straight line through one of these voids, you might cross 300 million light-years of space and encounter almost nothing. No galaxies, no clusters, just the faint, cold background of space itself. The Buddha's Void, one of the largest known, spans roughly 330 million light-years and contains only a handful of galaxies where you'd expect to find thousands. When astronomers first identified it in 1981, one of them reportedly said that if the Milky Way had been located in the center of the Buddha's Void, we wouldn't have known there were other galaxies until the 1960s. The void is that empty, that isolated. The filaments, by contrast, are where everything interesting lives, and some of them are enormous. The Sloan Great Wall is one filament in this cosmic web, identified using data from the Sloan Digital Sky Survey. It stretches approximately 1.37 billion light-years from end to end. For context, the entire Laniakea Supercluster, the structure containing our Milky Way, the Virgo cluster, and roughly 100,000 galaxies, spans about 520 million light-years. The Sloan Great Wall is more than twice that length, and it's just one filament among many in a much larger structure. But the Sloan Great Wall is not the largest. Astronomers have since identified a structure called the Hercules Corona Borealis Great Wall. It was detected through the distribution of gamma-ray bursts, the most powerful explosions in the universe. bright enough to be seen across nearly the entire observable universe, the Hercules Corona Borealis. Great Wall stretches an estimated 10 billion light-years. 10 billion. The observable universe is about 93 billion light-years in diameter, which means this single structure spans roughly a tenth of everything we can see. A filament so long that light, traveling at 186,000 miles per second, would take 10 billion years to cross it from end to end. That number is hard to sit with, but here's what makes it stranger. This structure didn't appear from nowhere. It grew. It was built, slowly and gradually, from something almost imperceptibly small. In the very early universe, matter was not perfectly uniform. There were tiny differences in density, regions where matter was ever so slightly more concentrated than the space around them. These weren't large fluctuations. We're talking about variations on the order of 1 part in 100,000. Barely anything. But gravity is patient, and the universe is old. Over hundreds of millions of years, the denser regions pulled in more matter. As they grew denser, they pulled harder. The slightly less dense regions around them were slowly stripped of their matter, growing emptier as their neighbors grew richer. Over billions of years, these tiny initial differences amplified into the web we see today. The filaments are where the overdense regions were. The voids are where the underdense regions were. The cosmic web is essentially a fossil record of the universe's earliest moments, written at a scale of billions of light-years. This means the structure of the web tells us something. When we map the filaments and measure the voids, we're reading information about conditions in the universe when it was less than 1 million years old. The pattern we see today was set then. The web is not just a description of where galaxies are. It's a record of where matter was, long before galaxies existed at all. Deep sky surveys have now mapped enough of the cosmic web that we can see the pattern clearly. The 2DF Galaxy Redshift Survey, the Sloan Digital Sky Survey, the VIPERS Survey. Each one images slices of the universe containing hundreds of thousands of galaxies, and each one reveals the same unmistakable structure. Filaments, nodes, voids. The web repeats at every scale we can measure. It is the organizing principle of the universe at its largest observable dimensions. And yet, for all its scale, the cosmic web fits within something larger still. Every filament we've mapped, every void we've cataloged, every supercluster and cluster and galaxy traced along those vast strands of dark matter and gas. All of it exists within the boundary of what we can actually observe. A web stretching billions of light-years in every direction, built from billions of years of gravity, working on tiny fluctuations in the density of a young universe. And all of it fits inside what we call the observable universe. The observable universe is 93 billion light-years across, contains roughly 2 trillion galaxies, and holds an estimated 10 to the power of 24 stars. That number, 10 to the 24th, is a 1 followed by 24 zeros. It's a quantity so large that it defeats most comparisons. But here's the one that tends to land. Scientists estimate there are roughly 10 to the 19th grains of sand on every beach and desert on Earth combined. That's 10 billion grains. The observable universe contains roughly 100,000 times more stars than that. Not more grains of sand on one beach. More than every grain of sand on the entire planet, multiplied by 100,000. The human mind simply wasn't shaped by evolution to grasp figures this vast. They're just symbols at that point. Here's something that confuses almost everyone the first time they hear it. If the universe is 13.8 billion years old, why is the observable universe 93 billion light-years across instead of 13.8 billion? The short answer is that the universe has been expanding the entire time. not expanding into something, not expanding outward from a central point. Space itself has been stretching, carrying everything in it along for the ride. And that changes the math in a way that most people never think about when they hear the phrase 13.8 billion years old. Let's walk through it carefully. When the Big Bang happened, the universe was extraordinarily small and extraordinarily dense. From that moment, space began expanding. Light began traveling. And those two things, the movement of light and the stretching of space, happened simultaneously, interacting in ways that aren't obvious. Light moves at 186,000 miles per second relative to the space around it. But if that space is itself stretching while the light travels through it, the light ends up reaching destinations that are farther away than a simple calculation would suggest. Much farther. Think about it this way. Imagine you're walking across a rubber band that someone is slowly stretching. You're moving forward at a fixed speed, but the band is getting longer under your feet. By the time you reach the other end, you've covered more total distance than if the band had stayed still. The light crossing the universe faces exactly this situation. It moves at constant speed through space, but the space it's moving through keeps getting bigger. Here's where the numbers get concrete. The best evidence we have for the earliest light in the universe comes from something called the cosmic microwave background. It's a faint glow of radiation filling the entire sky, the leftover heat from the early universe, detectable in every direction. That radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was so hot and dense that light couldn't move at all without being immediately absorbed. At 380,000 years old, the universe finally became transparent. When that light was released, the matter emitting it was roughly 42 million light-years away from the region that would eventually become our galaxy. That's close in cosmic terms. About 42 million light-years. But in the 13.8 billion years since that light was emitted, the space between us and that matter has expanded enormously. That same matter is now about 46 billion light-years away. The light it sent toward us has been traveling through stretching space ever since, and it's only just reaching us now. So when we detect the cosmic microwave background, we're seeing light that was emitted 42 million light-years away, but from matter that now sits 46 billion light-years from us. That's why the edge of the observable universe is 46 billion light-years in any direction. Roughly 93 billion light-years across in total. Not because light has traveled 46 billion light-years. It hasn't. It's because the space it traveled through kept stretching the whole time. This is the part that trips people up. It sounds like it shouldn't be possible. Nothing moves faster than light. That's one of the most fundamental rules in physics. So how can those galaxies be 46 billion light-years away if light only had 13.8 billion years to travel? The answer is that those galaxies aren't moving through space at superluminal speed. They're not violating anything. Space between us and them is expanding. The galaxies are sitting still relative to their local surroundings. It's the space itself that's growing, carrying them to greater and greater distances. That's an entirely different thing from motion through space, and it doesn't violate the speed of light at all. A useful way to think about it: draw two dots on a balloon. Neither dot is moving relative to the balloon's surface, but as you inflate the balloon, the distance between them increases. If you measured how fast the gap between those dots was growing, it could easily exceed any speed limit you set for things moving across the surface. The dots aren't moving. The surface is expanding. Galaxies in the universe work the same way, and this expansion isn't slowing down. That's the part that matters for what comes next. In 1998, astronomers discovered that the expansion of space is accelerating. Something is pushing it faster over time. Galaxies that are far enough away are already receding from us faster than light can close the gap between us. Their light will never reach us. They're already beyond our future reach, even though they're nominally inside the observable universe today. That boundary, the distance beyond which light can never reach us given the current and future rate of expansion, sits at about 16 billion light-years. Everything beyond that point is already lost to us in any practical sense, so the observable universe isn't a fixed sphere. It's a shrinking one in terms of what future observers will ever be able to see. Every year, more of the universe crosses beyond that threshold. Slowly, over hundreds of billions of years, the sky will empty out. Distant galaxies will redshift into invisibility. The cosmic microwave background will fade, and observers in the far future will have far less evidence available to them than we do now. The expansion of space isn't just a fact about the past. It's happening right now, pulling galaxies apart. And the consequences of that are stranger than almost anything else in cosmology. To understand why the universe is almost certainly far larger than the portion we can observe, you have to go back to its very first moments, and I mean the very first, within a tiny fraction of the first second. Not the first minute, not the first second. We're talking about a period so brief it has no meaningful analogy in human experience. In the first roughly 10 to the power of minus 35 seconds after the Big Bang, something extraordinary happened. The universe didn't just expand, it exploded outward at a rate that makes all subsequent expansion look calm by comparison. Physicists call this period inflation, and it's one of the most important ideas in all of modern cosmology. Here's what inflation actually means in physical terms. A region of space smaller than a single proton, smaller than any structure you could possibly point to, doubled in size, then doubled again, then doubled again. Roughly 85 times or more, each doubling happening faster than the last. By the time inflation ended, that microscopic region had expanded to something approximately the size of a grapefruit. That might not sound impressive. A grapefruit is not large. But the math behind it is almost incomprehensible. In an extraordinarily short interval, space expanded by a factor of at least 10 to the power of 26. After that, ordinary expansion took over, the slower, steady expansion that has continued ever since. The grapefruit-sized region eventually became the observable universe we can see today, 93 billion light-years across. But here's the part that most people miss. Inflation didn't just expand the region that became our observable universe. It expanded everything. Whatever volume of space existed before and during inflation was stretched by the same factor. Our observable universe represents only the tiny patch that happened to be in our vicinity. The rest of that expanded space is out there. We just can't see it, because light from those regions hasn't had time to reach us. And with expansion accelerating, it may never reach us. So how much larger is the whole universe than the part we can observe? The honest answer is that we don't know precisely. But physicists have made estimates based on the mathematics of inflation, and the numbers are staggering. Some models put the total universe at a minimum of 10 to the power of 23 times larger than the observable portion. That's 100 sextillion times larger. Others suggest it could be far bigger still. Some versions of inflation theory suggest the universe may be genuinely infinite, with no boundary of any kind. Our observable bubble, 93 billion light-years across, containing 2 trillion galaxies, would be, in that case, an almost invisibly small region of an unbounded whole. Now, why do physicists take inflation seriously? It wasn't invented just to make the universe bigger. It was proposed to solve several specific problems that had no other clean explanation. The first is what cosmologists call the horizon problem. When we look at the cosmic microwave background, the faint afterglow of the early universe, it's almost perfectly uniform in every direction. The temperature varies by only about 1 part in 100,000, but regions on opposite sides of the observable universe are so far apart that they could never have exchanged heat or information in the time available since the Big Bang. They shouldn't be the same temperature. They should be different, and yet they're not. Inflation explains this because those regions were once in contact. They were part of the same tiny, rapidly mixing patch before inflation stretched them apart. The uniformity we see today is a record of how close together everything once was. The second problem is flatness. The geometry of the observable universe is, as far as we can measure, almost perfectly flat. Not curved like the surface of a sphere, not saddle-shaped. Flat. This is strange because a universe that starts with even a small deviation from flatness will develop a growing curvature over time. For our universe to appear this flat after 13.8 billion years, it must have started out extraordinarily flat, far more than chance would suggest. Inflation solves this too. When you take any curved surface and expand it by a factor of 10 to the power of 26, the local geometry becomes indistinguishable from flat. The same way Earth's surface looks flat from where you're standing, the universe looks flat because inflation stretched away any large-scale curvature. The third piece of evidence comes from the specific pattern of density fluctuations in the cosmic microwave background. Those fluctuations, those tiny variations in temperature of 1 part in 100,000, have a very particular distribution. They match almost exactly what inflation predicts. Inflation takes quantum fluctuations, random variations at subatomic scales, and stretches them to cosmic scales. Those stretched fluctuations become the seeds of structure. They're the reason matter clumped into galaxies rather than spreading out uniformly. The pattern we see in the cosmic microwave background is essentially a photograph of quantum physics stretched to the size of the observable universe. That match between prediction and observation is one of the strongest pieces of evidence that inflation actually happened. And if inflation happened, the implications for size are inescapable. A process that expanded space by at least 10 to the power of 26 in a fraction of a second did not do so neatly, producing exactly the observable universe and nothing more. It produced vastly more space than what we can see. Our observable universe is the part we happen to inhabit. The rest extends outward in every direction, almost certainly for distances that make our 93 billion light-year sphere look like a single grain of sand on a very long beach. Our brains didn't evolve to hold numbers like that. There's no life experience that prepares you for scales of this kind. The best we can do is follow the mathematics, check it against the observations, and accept what the evidence points toward. The observable universe is not the universe. It's a window. And inflation tells us that the view through that window shows only a small portion of what's actually out there. Inflation produced the universe we observe, and almost certainly a great deal more. How much more is something cosmologists still argue about, but the lower estimates are staggering enough on their own. For most of the 20th century, astronomers assumed that while the universe was expanding, that expansion was slowing down. Gravity, they figured, had to be putting the brakes on. It made sense. The Big Bang sent everything flying outward. Gravity pulls matter together. So over billions of years, all that matter spread across the universe should be tugging on itself, gradually reducing the expansion rate, maybe eventually halting it entirely. That was the working assumption. It seemed almost obvious. The question astronomers were actually trying to answer in the late 1990s wasn't whether the expansion was slowing, it was how fast it was slowing. They wanted a number, so 2 independent teams set out to measure it. Both teams used the same tool, Type 1, A supernovae. These are stellar explosions that occur when a white dwarf star accumulates too much mass and detonates. The physics of the detonation is consistent enough that all Type 1a supernovae reach roughly the same peak brightness. That makes them useful. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. These supernovae are bright enough to see across billions of light years. They're one of the few tools astronomers have for measuring distances at that scale. Both teams measured dozens of supernovae. They compared nearby ones to distant ones. They crunched the numbers. And then both teams arrived at the same result, one that neither of them expected. The distant supernova were dimmer than they should have been. Not by a little. Consistently, measurably dimmer. That meant they were farther away than the models predicted, which meant the universe wasn't slowing down at all. It was speeding up. The expansion of the universe is accelerating. That result stunned the physics world. It was published in 1998. Both teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, confirmed the same finding independently. In 2011, the leaders of those teams received the Nobel Prize in Physics for the discovery. The question immediately became, what is pushing space apart? Gravity pulls. Nothing in the known universe pushes on this scale. There was no room in the standard model for a force that operated uniformly across all of space and counteracted gravity across hundreds of millions of light years. And yet here was the evidence, written in the light of distant supernovae. Astronomers gave this unknown force a name, dark energy. The name doesn't mean much. It's essentially a label for something we can detect by its effects, but cannot identify by its nature. Nobody knows what dark energy is. It doesn't emit light. It doesn't interact with matter in any way we can directly measure. It isn't dark the way dark matter is dark. It's something else entirely. And it's everywhere. What we do know is what dark energy does. It permeates all of space evenly at every point in the universe simultaneously. It exerts a kind of repulsive pressure, not a force pushing outward from any particular place, but a property of space itself that resists compression and drives expansion. The more space there is, the more dark energy there is, which drives more expansion, which creates more space, which creates more dark energy. It's self-amplifying, and its strength appears to be constant over time, at least so far as we can tell from current measurements. Here's what that does to our picture of the universe's contents. Ordinary matter, everything you've ever seen or touched, every planet, every star, every galaxy, every atom in your body, makes up about 5% of the universe. That's it, 5%. Dark matter, which is invisible but detectable through its gravitational effects on galaxies and galaxy clusters, makes up about 27%. And dark energy makes up the remaining 68%. We are built from a small minority component. Everything we've ever studied, everything science has ever examined directly, everything our instruments can actually detect, all of it adds up to roughly 1/20th of what exists. The dominant ingredient of the universe is something we can't see, can't measure directly, and have no satisfying physical explanation for. That's not a gap in our knowledge we expect to fill in next year. It's a fundamental unknown sitting at the center of modern cosmology. The cosmological constant is one candidate for what dark energy might be. Albert Einstein originally introduced it into his equations of general relativity as a kind of correction to prevent the universe from collapsing under its own gravity. He later called it his greatest blunder, after Hubble's observations showed the universe was expanding and no such correction seemed necessary. But if the cosmological constant represents the energy density of empty space, the vacuum energy, it could explain the accelerating expansion, Quantum field theory actually predicts that empty space should have energy. The problem is that the predicted value is off from the observed value by about 120 orders of magnitude. That's the worst prediction in the history of physics. Other candidates exist. Quintessence is a proposed form of energy whose strength varies over time and through space. Modified gravity theories suggest our understanding of gravity itself breaks down at cosmic scales. So far, none of these alternatives fits the data cleanly enough to displace the cosmological constant as the leading explanation. The honest answer is that we have a label and a measurement, but not an explanation. What dark energy means for the universe's future is significant. Because the expansion is accelerating rather than slowing, the universe won't collapse back on itself. It won't reach some maximum size and then reverse. It will keep expanding forever at an ever-increasing rate. Galaxies beyond a certain distance are already receding from us faster than light can travel through space to reach us. That boundary is moving closer all the time. Dark energy is the dominant ingredient of the universe. It's actively reshaping the cosmos on the largest scales, and we have almost no idea what it actually is. Here's something nobody tells you about the size of the universe. We're losing it. Dark energy is accelerating the expansion of space, and we've established that much. But there's a consequence of that acceleration that most people never hear about. It's not just that galaxies are moving away from us. It's that some of them are already gone. Not destroyed, not collapsed. Just gone from our sky forever. And we didn't notice when it happened. Here's how it works. As space expands, distant galaxies move away from us. The farther away they are, the faster they recede. This isn't galaxies moving through space at high speed. Space itself is stretching, and the more space there is between us and something else, the more stretching is happening, and the faster the gap grows. At a certain distance, that gap grows faster than light can cross it. Light from those galaxies is trying to reach us, but the space it's traveling through is expanding faster than the light can cover it. That light never arrives. It's not that the light slows down, it's that the destination keeps moving away faster than the light can close the distance. That threshold, the point at which galaxies become permanently unreachable by light, sits at roughly 16 billion light-years. Anything beyond that distance, if dark energy stays constant, will eventually vanish. Not all at once. Gradually over hundreds of billions of years, galaxy by galaxy. The light we're receiving from those distant objects right now is old light already in transit. Once the last of that light arrives, nothing follows. The source goes dark. Not because anything happened to it, but because the universe between us and it has stretched beyond what light can cross. Andromeda won't be one of those losses. At 2.5 million light-years, it's well within reach. In fact, as we've covered, it's moving toward us. It will collide with the Milky Way long before dark energy becomes a problem on that scale. The galaxies in our local group are gravitationally bound to us. They'll stay. But everything beyond the local group, everything outside the gravitational structures that hold us together, is drifting away on the expanding fabric of space. And the acceleration means it keeps drifting faster. The numbers matter here. Right now, there are galaxies we can observe that are already receding from us faster than light. We can still see them because the light they emitted long ago when they were closer is still reaching us. But new light they emit today will never get here. We're watching old signals from objects that have, in any meaningful sense, already left our observable universe. The 2 trillion galaxies astronomers count in the observable universe today is not a permanent number. It's a maximum. From here, that count only goes down. Imagine a civilization forming somewhere in our galaxy, not now, but 1 trillion years from now. Their sky looks very different. The local group has merged into a single enormous elliptical galaxy. Outside of that, there's almost nothing, no visible neighbors, no other galaxies within sight. The cosmic microwave background, that faint afterglow of the Big Bang, has been stretched so far by expansion that it's essentially undetectable. The evidence that the universe was once hot and dense and rapidly expanding is simply gone. There's no redshift pattern to study across large populations of galaxies because there are no accessible galaxies to study. There's no sign that space is expanding at all because everything observable is locked inside their own gravitational island. Those distant astronomers looking out with whatever instruments they have would conclude they live in a static, isolated universe. One galaxy, stable, eternal. They would have no way of knowing what we know right now. They could be brilliant, careful, methodical scientists and still arrive at a fundamentally wrong picture of the cosmos, because the evidence that would correct them no longer exists in their observable universe. That's not a small thing. We think of scientific knowledge as cumulative, as something that builds and sharpens over time. But the universe is actively erasing the evidence. The expansion of space is, slowly and irreversibly, stripping the night sky of the data future observers would need to understand their own reality. The cosmic web, the distribution of galaxies across billions of light years, the measurable expansion rate, the faint glow of the early universe, all of it requires a window of time to observe. That window is open now. It won't always be. We happen to exist at a moment when the universe is legible. The expansion is measurable. The galaxies are still there to count. The light from the early universe is still arriving. 13.8 billion years have passed since the Big Bang, and the evidence of that event is still detectable from this particular point in space and time. A few 100 billion years from now, it won't be. The universe will be just as large, probably larger, but far less readable. We exist at an unusually fortunate moment in cosmic history. The evidence for what the universe is and how it works is still visible to us, and that won't always be true. There's a number at the heart of cosmology called the Hubble constant, and right now, two of the best methods for measuring it are giving different answers. The Hubble constant measures how fast the universe is expanding. Specifically, it tells us how quickly galaxies are receding from us relative to their distance. For every megaparsec of distance, roughly 3.26 million light-years, galaxies are moving away from us at around 70 kilometers per second. That number sounds precise. It sounds settled. It isn't. Here's the problem. When astronomers measure the Hubble constant using the cosmic microwave background, the ancient light left over from the early universe, they get a value of about 67 to 68 kilometers per second per megaparsec. When they measure it using Cepheid variable stars and Type 1a supernovae in the nearby universe, they consistently get about 73 to 74. That gap is roughly 8 to 10%. It doesn't sound like much, but in cosmology, it's enormous. Both measurements are careful. Both have been checked and rechecked. Both are peer-reviewed and reproduced by independent teams using independent data. They aren't preliminary results from a single study. They represent decades of cumulative work, refined instruments, and increasingly precise techniques. And they still disagree. The cosmic microwave background method works backward. Astronomers measure the pattern of temperature fluctuations in this ancient light, fit those measurements to the standard cosmological model, and extract a predicted expansion rate. It's essentially asking, given how the universe looked 380,000 years after the Big Bang, how fast should it be expanding today? The Cepheid and supernova method works forward. Cepheid variable stars pulse at rates that are directly tied to their true brightness. Measure how bright they appear from Earth, compare that to how bright they actually are, and you get their distance. Do this for nearby galaxies. Then use those galaxies to calibrate the brightness of Type 1a supernovae, explosions so luminous they can be seen across billions of light years. Use the supernovae to measure expansion rates across vast distances. The answer you get is about 73 to 74. Two methods, two different eras of the universe they're sensitive to, two different answers. This is the Hubble tension. Astronomers have spent years looking for the mistake. Maybe the Cepheid measurements are contaminated by dust between stars. Maybe there's a systematic error in how the supernova brightness is calibrated. Maybe the early universe model has a flaw baked in. None of these explanations have held up. Every time a potential error is identified and corrected, the tension remains. This matters beyond the specific number. The Hubble constant sets the scale for the entire observable universe. It determines how we calculate distances to remote galaxies. It shapes our estimate of the universe's age. A higher value suggests a somewhat younger universe. A lower value suggests older. If the true number differs meaningfully from what we've assumed, then our maps of the cosmos, every distance calculation that depends on the expansion rate, could be systematically off. What could explain the disagreement? Several possibilities. One is that dark energy isn't actually constant. If it varied over time, stronger in the early universe, weaker now, or vice versa, the two measurement methods would naturally produce different values because they're sensitive to different epochs. Some physicists call this early dark energy, a form that was present in the first fraction of the universe's history and then faded. Another possibility involves extra species of neutrinos, lightweight particles that flooded the early universe. A slightly different neutrino count would change how fast the early universe expanded, shifting the cosmic microwave background prediction upward. There are more exotic proposals, a fifth fundamental force operating only on certain scales. Interactions between dark matter and dark energy that our standard model doesn't account for. Small-scale errors in how we model the neighborhoods around Cepheid stars. The list of candidates is long, and none of them is confirmed. What makes the Hubble tension genuinely significant, rather than just a technical dispute between specialists, is that it might be pointing at new physics. The standard cosmological model is extraordinarily successful. It predicted the cosmic microwave background pattern before it was measured in detail. It correctly described the abundances of light elements produced just after the Big Bang. It predicted the large-scale structure of the cosmic web. For that model to be giving one expansion rate while direct observation gives another is the kind of crack that has historically preceded major revisions in physics. The discrepancy between Newtonian mechanics and the orbit of Mercury was also small in absolute terms. It pointed to general relativity. The James Webb Space Telescope has now entered this conversation. It has independently checked some of the Cepheid distance measurements that underlie the higher expansion rate. Early results have confirmed the tension rather than resolved it. The gap is still there. If anything, it's become harder to dismiss. The Hubble tension is either a crack in our instruments or a crack in our understanding of the universe, and astronomers can't yet tell which one it is. The James Webb Space Telescope was designed to look back farther in time than any instrument before it. And within its first few years of operation, it found galaxies from a universe we barely recognize. To understand what that means, you have to understand what the telescope is actually doing. It isn't looking at distant objects the way you'd look at something far across a field. It's looking back in time. Light travels at a fixed speed. It takes time to cross space. The light arriving at Webb's mirrors right now left its source billions of years ago. So when Webb detects a galaxy at extreme distance, it's seeing that galaxy as it existed in the deep past, not as it is now, as it was. The most distant confirmed galaxy Webb has observed is called JADES-GS-Z 14-0. The name isn't memorable, the numbers behind it are. This galaxy existed just 290 million years after the Big Bang. Its light has been traveling toward us for approximately 13.5 billion years. That's long enough that the universe was still, by cosmic standards, an infant when this light began its journey. There were no planets around most stars. There were barely any stars at all. The universe was only starting to pull itself together out of hydrogen and helium and darkness. But here's where the numbers get strange. That galaxy isn't 13.5 billion light-years away. It's roughly 33 billion light-years away. Space expanded while the light was traveling. The galaxy moved. Not through space, but with space, carried outward by the expansion of the universe itself. The light kept crossing the distance, but the destination kept receding. After 13.5 billion years of travel, it finally reached us, and the source is now 33 billion light-years distant. A number like that doesn't fit neatly into any human frame of reference. It's just mathematics at that point. Real mathematics describing a real place that we'll never reach. What Webb found in that galaxy and in others like it is what's keeping cosmologists up at night. JADES-GS-Z14-0 is bright. It's large. It contains far more stars than it should. According to the models astronomers have spent decades refining, a galaxy 290 million years after the Big Bang shouldn't have had nearly enough time to build that much structure. Stars form slowly. Galaxies accumulate mass gradually. The process takes time. And 290 million years in cosmic terms isn't much time at all. Our sun alone took about 50 million years to form from its parent cloud of gas. Building billions of stars, organizing them into a coherent galaxy, growing massive enough to show up clearly in our instruments. That's supposed to take longer. Much longer. And yet, there it is. This isn't an isolated case. Webb has found multiple early galaxies that are too bright, too massive, too structured for their age. Not one anomaly that could be explained away. A pattern. And patterns don't go away when you look harder. Usually they sharpen. Some astronomers have proposed explanations. Maybe the early universe formed stars more efficiently than current models predict. Maybe the first stars were significantly more massive than stars forming today, burning brighter and dying faster, seeding galaxies with material more quickly. Maybe something about the early universe's conditions accelerated structure formation in ways our simulations don't fully capture. These are real possibilities under active investigation. None of them have been settled. The other possibility is harder to dismiss. The models are wrong in a more fundamental way, not wrong in small details, but wrong about something structural. If galaxies formed this quickly this early, then our understanding of the early universe's timeline and initial conditions may need serious revision. And revising those initial conditions doesn't just change early galaxy formation, it changes the whole picture. The size of the universe, the rate of its expansion, the way matter was distributed after the Big Bang, all of these are connected. Pull on one thread and others follow. Webb wasn't supposed to find things that couldn't be explained. It was supposed to confirm and sharpen what we already knew, seeing clearly what previous telescopes could only detect faintly. Instead, within its first few years, it's delivering observations that don't fit. That's not a failure of the telescope. That's science working the way it's supposed to. You build the best instrument possible, you point it at the universe, and you let the universe tell you whether your assumptions were correct. The answer so far is that some of them weren't. There's something worth pausing on here. We're looking at a galaxy that formed 290 million years after the Big Bang. The light from that galaxy is 13.5 billion years old. And what that ancient light is telling us is that we don't fully understand what was happening when it left. The universe, even after decades of careful observation, still has the ability to surprise us at its edges. Not with small surprises, with fundamental ones. Webb is still early in its mission. It has years of observations ahead, more distant galaxies to find, more spectra to analyze. The record holder today may not be the record holder a year from now. Each new detection is another data point. Each data point either fits the model or it doesn't. Right now, a meaningful number of them don't. JWST has been operational for only a few years, and it's already forcing cosmologists to revise models they spent decades building, which is both exciting and a little unsettling. Everything we've talked about, the Milky Way, the local group, Laniakea, the cosmic web, the full 93 billion light-year span of the observable universe, all of it fits inside what might be a relatively small region of a much larger whole. That's not a metaphor. It's the actual implication of the physics we have right now. The observable universe has a boundary, but that boundary isn't a wall. It's not an edge where space stops. It's simply the distance light has been able to travel since the universe became transparent to light about 380,000 years after the Big Bang. Beyond that distance, there is almost certainly more. The question is, what kind of more? There are a few possibilities. The first is the simplest. The universe could be larger than what we can observe, the same kind of space, the same laws of physics, the same distribution of galaxies and filaments and voids, just extending much further in every direction than we can see. No exotic new physics required, no parallel realities. Just more universe. Some estimates, based on the geometry of space revealed by the cosmic microwave background, suggest that if the universe is finite, it's at least 10 to the power of 23 times larger than our observable portion. That's a 1 followed by 23 zeros. Our observable universe, all 93 billion light-years of it, would represent a smaller fraction of the total than a single proton represents compared to the observable universe itself. The numbers stop meaning anything at that point. They become symbols on a page. The second possibility comes directly out of inflation theory. When inflation ended in our region of space, it may not have ended everywhere. Some models predict that inflation is eternal, that beyond our cosmic horizon, space is still undergoing that exponential expansion. And where inflation eventually does stop in different regions, the conditions at the end of inflation determine the local physics. The temperature, the strength of the fundamental forces, the mass of particles. In this picture, our universe is a bubble, a region where inflation happened to end, and where the resulting physics happen to allow atoms, stars, and galaxies to form. Surrounding our bubble, eternally inflating space continues to generate new bubbles, each with its own physics, its own constants, its own Seibel versions of reality. This is called eternal inflation, and it produces what physicists call a multiverse, not as a science fiction concept, as a genuine consequence of a theory that explains several otherwise puzzling features of our universe. The uniformity we see across the sky, the flatness of space, the specific pattern of fluctuations in the cosmic microwave background. Inflation accounts for all of these. And if inflation is real, eternal inflation may be a natural result. There's no way to test this directly. We can't see other bubble universes. They're causally disconnected from us. Light from them can never reach us. If they exist beyond any horizon we will ever be able to observe. That doesn't make the idea wrong. It just makes it difficult. Some physicists find this deeply troubling. A theory that makes no testable predictions is hard to call science in the traditional sense. Others argue that eternal inflation does make indirect predictions about the statistics of physical constants we observe in our own universe. The debate is ongoing. The third possibility is the most vertiginous. The universe might be infinite, not large, not vast, genuinely, literally infinite, extending forever in every direction with no boundary and no edge. This is actually consistent with everything we currently observe. The cosmic microwave background data suggests that space is geometrically flat or very close to it. A flat geometry can extend infinitely. We can't confirm infinite size from inside a finite observable region, but we can't rule it out either. And if the universe is infinite, the implications are staggering in a way that's hard to sit with. In an infinite universe, every possible arrangement of matter that the laws of physics permit eventually occurs. Somewhere, separated from us by a distance so large it makes our observable universe look like a dust grain, there is a region of space identical to ours. Same galaxies, same solar system, same planet, same conversation. And beyond that, every possible variation. The physics here isn't mystical, it's combinatorics. Finite configurations of matter repeated across infinite space. The repetition is mathematically guaranteed. Our brains didn't evolve to process any of this. That's worth saying plainly. The discomfort you might feel trying to hold an infinite universe in your head isn't a failure, it's appropriate. These aren't numbers we have any frame of reference for. What we can say honestly is this: the observable universe is not the universe. It's a window, a small, finite sphere centered on wherever you happen to be standing, bounded not by the edge of reality, but by the speed of light and the age of the cosmos. Everything beyond that window is still real, still there. We simply cannot see it, and depending on how dark energy behaves over the next hundreds of billions of years, we may see less and less of it as time goes on. We've measured 93 billion light-years of universe and found it to be staggeringly large, and the honest answer from cosmology is that this is almost certainly the smallest the universe gets. So let's come back to Earth for a moment. Earth is a rocky planet about 8,000 miles across. It orbits an ordinary star, one of somewhere between 100 and 400 billion stars in the Milky Way. The Milky Way is one of roughly 2 trillion galaxies in the observable universe. And the observable universe is almost certainly a small fraction of everything that exists. That's where you live. That's where all of this is happening. We started with the Moon, 240,000 miles away, 3 days by spacecraft, a distance that felt enormous until we set it next to the solar system, and it shrank to nothing. Then we moved out to the Sun, 93 million miles from Earth, 8 light minutes. Then Neptune, 2.8 billion miles out, where a radio signal takes 4 hours to arrive. Then the Oort cloud, 2 light-years from the Sun, and we haven't reached it yet with anything we've launched. Voyager 1 has been flying for nearly 50 years. It's covered 15 billion miles. It's still essentially in our backyard. Then we crossed into interstellar space. Proxima Centauri, the nearest star, sits 4.24 light-years away, 25 trillion miles. The light you'd see from it tonight left 4 years ago. At Voyager's speed, reaching it would take 75,000 years. Not miles, years. Then the Milky Way opened up around us, 100,000 light-years across, hundreds of billions of stars, and our solar system sitting quietly about 27,000 light-years from the center. The last time we were in this same position in our orbit around the galaxy, dinosaurs were just beginning to appear on Earth. Then the local group. Dozens of galaxies spread across 10 million light-years, the Andromeda galaxy 2.5 million light-years away, its light beginning its journey before modern humans existed. Then Laniakea, 520 million light-years of galaxies drifting toward a gravitational center we call the Great Attractor. Then the cosmic web, filaments stretching 1 billion light-years, voids hundreds of millions of light-years across containing almost nothing. And finally, the observable universe itself, 93 billion light-years in diameter, 2 trillion galaxies, roughly 10 to the power of 24 stars, a number that exceeds every grain of sand on every beach and desert on Earth. And beyond that, almost certainly, vastly more. Now here's the thing. The size of all of this is not the remarkable part. Of course, the universe is enormous. There's no reason it had to be small. Stars form, galaxies form, structures grow, space expands. And after 13.8 billion years, you end up with something incomprehensibly large. That's not the surprising part. The surprising part is this. On one small planet, orbiting one average star, in one ordinary galaxy, matter arranged itself into something that could figure all of that out. We detected the cosmic microwave background, the faint afterglow of the Big Bang still washing over us at 2.7 degrees above absolute zero. We photographed galaxies from when the universe was only 290 million years old, light that had been traveling for 13.5 billion years before landing in a telescope we built and launched from this planet. We measured the expansion of space itself. We found that 68% of the universe is made of something we can't see or identify. We mapped Laniakea, a supercluster 520 million light-years across, and figured out where we sit inside it. We did all of that from here. Our brains didn't evolve for any of this. They evolved for faces, for food, for immediate threats on the African savanna. They weren't built to hold numbers like 10 to the power of 24, or distances like 46 billion light-years, or timescales like 13.8 billion years. And yet we built the instruments and the mathematics and the methods to reach those numbers anyway. We extended our senses across scales our biology was never designed for. You will not be able to hold the full scale of the universe in your mind at once. Nobody can. You can say the words. You can write the numbers. But the actual felt sense of what 93 billion light-years means, what 2 trillion galaxies means, what a possibly infinite universe means, that doesn't fit inside a human brain. It probably never will, but that's not the same as not understanding it. You understand it differently than you understand where your keys are. It's a structural understanding. You know the shape of it, even if you can't feel the size. You know the moon is close, the sun is farther. The nearest star is incomparably farther still. The galaxy is 100 times farther than that, and the observable universe extends 1 billion times farther than the galaxy. You know where you are in the chain, and knowing where you are in the chain is real knowledge. It changes something. Look up at the night sky, and the stars aren't just lights anymore. They're distances, they're time. The light leaving Andromeda right now will arrive here in 2.5 million years. The light you see from it tonight left before your species existed. Every star you can see with your eyes is somewhere between 4 years and thousands of years in your past. The sky is not a ceiling, it's a record. And somewhere beyond the farthest thing we've ever seen, beyond the edge of what any telescope can reach, space continues. How far? We don't know. Whether it ends, we don't know. Whether there are other regions with different physics, different constants, we don't know. These are open questions, real ones, and the people working on them are alive right now and building better instruments. We are small. That part is settled. A planet orbiting a star, inside a galaxy, inside a supercluster, inside a web, inside an observable universe that is itself almost certainly a small region of something larger. Small in every direction and at every scale, but we've measured it. That's what's strange. That's what doesn't follow. The universe doesn't need us to comprehend it to be magnificent, but we're here anyway, looking up, measuring what we can. And that turns out to be its own kind of wonder.